It's late. The day is finally behind you. You're ready for something quiet, something calm, but still interesting enough to keep your mind gently awake. So tonight, instead of drifting off with the same old thoughts, you're going to take a short step beyond your familiar sky. And here's the part most people never hear. Within just 16 light years of the Sun, a distance that is tiny on galactic scales, there are nearly 50 star systems and more than 60 stars and substellar objects, a full neighborhood, a cosmic block, and almost none of them look like the Sun. That's the first twist. The Sun, the star you grew up with, the one you assume is typical, is actually an outlier. Most of our closest neighbors are smaller, dimmer, more active, or even already dead. Sarah Seeger once said, "Most stars in the Milky Way are small, dim red dwarfs." And in our immediate neighborhood, that statement becomes very real, because hidden in this tiny sphere around us, a region you could cross with a future interstellar probe in a human lifetime, are some of the strangest objects in our galaxy. Let me give you 6 quick glimpses. 6 small wow moments to open the door. 1. Proxima Centauri, the nearest star, can unleash flares strong enough to strip the atmosphere off an entire planet. A star so small, yet so violently unpredictable, it would turn any nearby world into a battlefield of radiation. 2. Alpha Centauri, the famous double star, offers something cinematic. 2 suns rising and setting together. A real physical 2-star sky, not science fiction. 3. Sirius, the brightest star in our night sky, hides a secret right beside it. A collapsed stellar core. A white dwarf, Sirius B, so dense that a teaspoon of its material would weigh tons. Beauty, with a ghost orbiting it. 4. Wolf 359, one of the faintest stars near us, is a red dwarf so long-lived it will continue burning long after the Milky Way has changed beyond recognition. A tiny ember, outliving entire eras of cosmic history. 5. Ross 128b, one of the closest potentially temperate exoplanets, orbits its star in just 9.9 days, yet still receives almost the same amount of light as Earth. A world that races around its sun, but might still be calm enough to keep an atmosphere. 6. And Gliese 581g, the planet once hailed as Earth 2.0, sparked worldwide excitement, until later studies suggested it may not exist at all. A reminder that even in our cosmic backyard, we are still learning how to see clearly. So here's the real question to begin our journey. What if the strangest things in our galaxy are not billions of light years away, but right next door? Tonight, we're not traveling to the edge of the universe. We're not diving into quasars or black holes or the earliest galaxies. We're simply stepping outside the solar system onto the front porch of our cosmic home and meeting the neighbors, each with a personality. Proxima, the violent neighbor. Alpha Centauri, the 2-sun dream. Barnard star, the old sprinter. Wolf 359, the eternal ember. Sirius, the bright dog and the ghost. Ross 128, the quiet haven. Gliese 581, the Earth 2.0 mirage. These stars are the first destinations future missions may one day reach. Laser sailcraft, nanoprobes, interstellar scouts built not for sci-fi, but for the coming centuries of real exploration. And before you drift off tonight, you'll see exactly why scientists believe our quiet little neighborhood isn't quiet at all. Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to you. But tonight, it might make just a little more sense than it did yesterday. So relax, settle in, because your mind is about to leave the solar system very gently. To understand all of them, we begin with the only star we truly know, our sun. Before we travel into the neighborhood beyond the solar system, there's one star we must understand completely. Not because it's the biggest, not because it's the strangest, but because it is home. The star that defines every distance, every temperature scale, and every comparison we'll make from this point forward. The Sun is a G2V main sequence star, a stable, middle-aged fusion engine about halfway through its 10 billion year life. For all of human history, it has been the one constant: rising, setting, warming oceans, stirring weather, and anchoring every orbit around it. And yet, as simple as it looks from Earth, the Sun is far from simple. The astronomical unit, the first ruler of the universe. Astronomers needed a number that made sense, something practical. So they built a ruler based on home. 1 astronomical unit, or 1 AU, is the distance from Earth to the Sun, about 149.6 million kilometers, or 93 million miles. A distance so large that sunlight, the same light that shines on your driveway every morning, takes 8 minutes and 20 seconds to arrive. Every sunrise you've ever seen is already 8 minutes old. That delay becomes important because throughout this journey, AU is our baseline. Every star, every orbit, every habitable zone will be measured in multiples of this familiar scale. The first step beyond home. If you could fly downward through the Sun, imagine descending into the Sun layer by layer, not melting, just observing, the way spacecraft like Parker's Solar Probe try to do in their own limited way. You would pass through 6 distinct regions. 1. The core, a 15 million Kelvin furnace where hydrogen fuses into helium. Here, a single photon begins a journey that will take up to 100,000 years to escape. 2. The radiative zone, dense, still, and unimaginably slow for light. Photons scatter again and again, moving only inches at a time. 3. The convective zone energy now rises and sinks like boiling water. Huge columns of plasma churn, shaping magnetic fields. 4. The photosphere, the surface at 5,800 K. This is the layer you see with your eyes, the place where sunspots form. 5. The chromosphere, a thin, reddish band revealed during eclipses. 6. The corona, the ghostly outer atmosphere stretching millions of miles outward, reaching over 1 million Kelvin. And this is where one of astronomy's greatest mysteries appears. Why is the corona hotter than the surface below it? The photosphere is 5,800 K. The corona is 1-2 million K. It shouldn't work that way, and yet it does. Even with our most advanced probes, the coronal heating problem remains unsolved. A reminder that the star we think we know best still holds secrets. The Sun's 11-year heartbeat. Every 11 years, the Sun transitions from quiet to active and back again. It's a rhythm Earth has lived under long before humans evolved. During active phases, sunspots multiply, magnetic fields twist, solar flares erupt, and coronal mass ejections burst outward. A sunspot is a cooler, darker patch caused by intense magnetic fields restricting the flow of heat. Where sunspots appear, storms often follow. Solar flares and CMEs fling high-energy particles across the solar system. When they reach Earth, they can create auroras, disrupt satellite communications, affect GPS accuracy, and in rare cases, nudge power grids. You may not feel it day to day, but much of the technology around you, your phone's GPS lock, the satellite TV signal, even the timing systems in financial networks, depends on a stable sun. The solar wind, a constant breath. Even on its calmest days, the sun exhales a steady stream of particles called the solar wind, traveling 400–800 km/s. This wind shapes an enormous bubble, the heliosphere, that extends far past Pluto. Inside it, the sun's influence dominates. Outside it, the galaxy begins. One day, when humanity launches probes toward the nearest stars, the first milestone they'll cross won't be a planet, but the boundary where the solar wind fades into interstellar space. Our spacecraft ambassadors. To understand the sun, we've sent a fleet of spacecraft that watch it every hour of every day. SOHO observes solar storms and eruptions. SDO captures high-resolution images of the corona. Solar Orbiter tracks magnetic fields and flows. And the Parker Solar Probe dives directly into the corona itself. Its mission team put it simply, we're literally touching the sun. Parker now travels faster than any spacecraft in history, reaching speeds over 700,000 km/h as it skims the sun's outer atmosphere. Data from these missions helps us understand not only the sun, but also how other stars might behave, especially the violent ones, a stable anchor in a chaotic galaxy. Despite all this activity, the sun is remarkably calm compared to most stars around us. It contains 99.8% of the mass of the entire solar system. It drives every tide, every season, every weather pattern, every tree, every breath of air, every heartbeat on Earth ultimately traces back to fusion in its core. And yet, here's the twist. The sun is not a typical star. It is brighter than most nearby stars, larger than most, and far less violent. In the neighborhood we're about to visit, the sun stands out, not because it's extreme, but because it isn't. That's why this segment matters. Now that you understand the star we call home, you'll start to see just how different, how wild our neighbors really are. We've spent long enough at home. Let's meet the one that lives right next door. When you step beyond the gentle reach of the sun and into true interstellar space, the first star waiting for you is Proxima Centauri. Just 424 light-years away, Proxima is our closest stellar neighbor, a small, cool M5.5V red dwarf with only 12% of the sun's mass and 14% of its radius. It emits less than 0.2% of the sun's light, so faint that you could stare directly at its location in the sky and never notice it. And yet, despite its dim glow, Proxima is anything but quiet. A tiny star with explosive behavior, Proxima Centauri is an active flare star, meaning its magnetic field twists and snaps with intense instability. When it releases energy, it does so violently, with sudden bursts of X-ray and ultraviolet radiation that can outshine its normal brightness in minutes. One of the most dramatic events happened in 2018, when astronomers observed a super flare so powerful that Proxima's brightness surged by 68 times, and its X-ray emissions rose nearly 1,000-fold for several minutes. To put that into perspective, if the sun erupted like Proxima does, every satellite we've ever launched would be fried instantly. This is why Proxima is often described as a star that looks harmless from afar, but behaves like a live wire. If you could hover above Proxima's surface, the star would appear dull red, almost sleepy. But that calm would last only until the next magnetic snap, a sudden eruption bright enough to scorch any nearby world. Standing near it would feel like standing next to a barely glowing coal that randomly turns into a blowtorch. This is why Proxima earns its title, the violent neighbor. Proxima b, the almost Earth that might not survive. In 2016, astronomers discovered something extraordinary, a planet, Proxima b, orbiting inside the star's habitable zone. It has a minimum mass of 1.17 Earth masses and orbits once every 11.2 days, receiving about the same total energy as Earth does. On paper, it looked like the best news in decades, a potentially temperate world, extremely close and reachable by future probes. But the deeper the data went, the less ideal the picture became. Because the same flares that make Proxima dangerous also make it hostile. Radiation storms, plasma outflows, and stellar winds can erode atmospheres over time. Simulations show that without extraordinary protection, much stronger than Earth's magnetic field, an atmosphere around Proxima b could be stripped away in a few 100 million years. Here's the sharper truth. It looks Earth-like on paper, but physics doesn't care about appearances. Proxima b is almost certainly tidally locked, with one side scorched in perpetual daylight and the other trapped in endless night. If it once had an atmosphere, it may now be thin, damaged, or gone. It is a world caught between possibility and harsh reality. And yet, the idea that such a world exists right next door is still compelling. Because even if Proxima b is rough, the system itself is our first real stepping stone to the stars, other possible planets, and the noise of a noisy star. You may hear about Proxima c or Proxima d, but their existence remains debated. Proxima's magnetic activity creates signals that mimic planetary signatures, making it extremely difficult to separate real planets from stellar noise. Even at the closest star system, the cosmos reminds us, seeing clearly is harder than it sounds. Breakthrough starshot, reaching Proxima within our lifetime. Here is the part that instantly sparks the imagination, especially for anyone who grew up watching science fiction. Breakthrough starshot is a proposal to send tiny spacecraft to Proxima Centauri using ground-based lasers that push ultra-light light sails to speeds of 0.2 c, 20% the speed of light. At that velocity, a probe could reach Proxima in 20-30 years. Not millennia, not centuries, but within the span of a single human life. Avi Loeb summarized it perfectly. Starshot could turn interstellar travel from science fiction into science fact. There are challenges, of course: navigation, communication, miniaturization. But each one is a challenge of engineering, not impossibility. Even the risk of interstellar dust is manageable. At 0.2 c, a grain of sand is dangerous, but the probes would be microscopic, fast, redundant, and built in swarms. A few may fail, but a few might succeed. And if even one arrives, humanity will have touched a star. Because for the first time, it's not fantasy, it's plausible. A member of a larger family, Proxima, is part of the Alpha Centauri triple system, loosely bound alongside Alpha Centauri A, Alpha Centauri, BA, and B form a tight binary. Proxima orbits far beyond them in a long, slow arc that takes hundreds of thousands of years. That makes Proxima the closest star to us at the moment. But in cosmic time, it drifts. One day, perhaps millions of years from now, another star may take its place as the nearest. For now, though, this is our closest neighbor. Small, dim, and explosively active. A star that reminds us that proximity does not mean safety. Proxima may be weak in light, but in personality, it is overwhelming. And it sets up the perfect contrast for what comes next. And if the closest star can be this extreme, what might be waiting as we move deeper into the neighborhood? But if Proxima is the violent neighbor, the next star system is the dream home of science fiction. If Proxima Centauri is the violent neighbor, small, dim, and unpredictably explosive, then the next stop on our journey feels like a completely different world. A place that looks calmer, brighter, and far more familiar. A place that, if humanity ever settles beyond the solar system, might be the first real candidate for a second home. Just beyond Proxima, at 437 light-years, lies Alpha Centauri. Not one star, but two. Alpha Centauri A and Alpha Centauri B form the closest binary star system to Earth. Two suns orbiting each other in a gravitational dance that lasts roughly 80 years. At their closest, the two stars approach to about 11 AU, and at their farthest, they drift apart to 35 AU. From far away, they seem peaceful, predictable, stable, a stark contrast to the volatility we just left behind. But they are far more than that. They represent something almost dreamlike, a place where two suns could rise and set in the sky of a real physical world. Not science fiction, not CGI. A genuine astronomical possibility. Two stars, two personalities. Let's start with Alpha Centauri A, the larger of the pair. It's a G2V main sequence star, just like our Sun, but slightly bigger, around 1.1 times the Sun's mass, and shining at about 1.5 times the Sun's luminosity. Bright, stable, and familiar. Its companion, Alpha Centauri B, is smaller, a K1V orange dwarf, with roughly 0.9 times the Sun's mass and about half the Sun's brightness. A is like a warm, steady campfire. B is a smaller, gentler flame beside it. Together, they form a binary system that has fascinated astronomers for generations. And for good reason. Both stars are shockingly stable compared to most red dwarfs in our neighborhood. In a galaxy filled with chaotic flares, magnetic storms, and extreme variability, the Alpha Centauri pair stands out as an island of order. The orbital dance. Their gravitational orbit is wide and slow. Period. 80 years. Closest separation. 11 AU. Farthest separation. 35 AU. From a hypothetical world orbiting one star, the other would drift across the sky, sometimes appearing fairly close, other times distant, like a second sun slowly moving along a multi-decade arc. And here's the detail that captures people's imagination. If you stood on the surface of a stable planet in this system, you would see two suns rising and setting, not in a fantasy movie, in reality. The binary sunset scene from Star Wars resonates so deeply because it taps into something human. The idea that alien worlds can still feel warm, familiar, and beautiful. Alpha Centauri offers that possibility. Could planets survive here? For decades, astronomers wondered whether a stable planetary system could exist in a binary star environment. Two massive bodies pulling in different directions complicate things, especially over billions of years. But simulations show that stable orbits absolutely exist. Planets can orbit close around A without being disrupted by B. Planets can orbit close around B without being disrupted by A. The only truly unstable region is the wide middle zone between the two stars. This means an Earth-like world could plausibly exist around either star, tucked into a tight, stable orbit, where the companion star simply becomes a bright object in the sky. Didier Queloz, Nobel laureate, once put it simply: binary stars do not forbid planets, they simply complicate them. And Alpha Centauri is the perfect example. The search for planets, a story of excitement and frustration. In 2012, a claim emerged: Alpha Centauri BB, an Earth-sized world orbiting extremely close to Alpha Centauri B. The astronomy community exploded with excitement, but the signal eventually turned out to be noise from the star itself. Then, in 2021, a new candidate appeared, a possible planet seen in infrared data, again orbiting Alpha Centauri A. It was promising, but still unconfirmed. This is the twist. We suspect planets may exist here. We have hints. We have signals. But we do not yet have certainty. And in astronomy, uncertainty is a normal part of the discovery process. Each new instrument, each new telescope, gets us a little bit closer to clarity. Why Alpha Centauri remains humanity's favorite second home candidate? There are 3 reasons. 1. Stability. Both stars are main sequence and unusually calm for their age. Their luminosities change slowly. Their habitable zones are predictable. 2. Distance. At just 4.37 light-years, Alpha Centauri is practical. With future propulsion methods, even slow ones, it becomes reachable. 3. Familiarity. Alpha Centauri. A is nearly a twin of the Sun. For life as we understand it, that matters. If humans ever build interstellar probes capable of capturing high-resolution images of alien landscapes, Alpha Centauri would be the first place we point them. And long before probes arrive, Alpha Centauri has already entered our culture. In James Cameron's Avatar, the planet Pandora orbits Polyphemus, a gas giant in the Alpha Centauri A system. Science fiction chose Alpha Centauri not because it's exotic, but because it feels like the place where a second Earth should logically exist. The telescopes that will decide the truth. Over the next few decades, several instruments may finally reveal whether planets truly orbit these stars. JWST, capable of infrared detection and atmospheric characterization. The Extremely Large Telescope, ELT, with adaptive optics powerful enough to directly image nearby planets. The Habitable Worlds Observatory, NASA's planned mission to search for Earth-like worlds around Sun-like stars. These observatories will hunt for planetary signals, analyze spectra, and search for the faint fingerprints of atmospheres, water vapor, oxygen, methane, or combinations that suggest chemical imbalance. If a habitable planet exists around Alpha Centauri A or B, the 21st century has the tools to find it. And if such a planet is discovered, it would immediately become one of the most important worlds in the galaxy. The emotional core of Alpha Centauri. Where Proxima is chaotic, Alpha Centauri feels stable. Where Proxima flares, Alpha Centauri warms. Where Proxima threatens, Alpha Centauri reassures. This system gives something rare in astronomy: hope. The hope that somewhere, Not too far from here, there could be a world warm enough, bright enough, and calm enough to support life. A world with two suns rising gently in its sky. A world that feels like home and wonder at the same time. And as we leave this bright, balanced pair behind, the journey shifts once again, moving towards something older, quieter, and surprisingly fast. Because beyond this dreamlike system lies our next destination, a star that races across the sky faster than almost any other. Leaving Alpha Centauri behind, the neighborhood grows quieter. The stars become smaller, dimmer, older, and in their subtlety, they reveal something different about our part of the galaxy. The next stop is a star that almost never draws attention, until you learn what makes it special. Barnard's star. At about 596 light-years away, it is the fourth closest individual star system after Proxima and the Alpha Centauri trio. It is an M4V red dwarf, carrying only about 0.14 times the Sun's mass and 0.2 times the Sun's radius. Its luminosity is just 0.004 that of the Sun, less than a 20th of 1%. To the naked eye, Barnard's star is invisible. To a telescope, it is faint. To the galaxy, it is small. But to astronomers, it is remarkable. Because Barnard's star is old. Very old. An ancient red dwarf still burning. Estimates place its age between 7 and 12 billion years, meaning it formed when the Milky Way was still settling into its shape. Compared to the Sun's 4.6 billion years, Barnard's star is an elder, and it will keep glowing for trillions of years to come. Where massive stars live fast and die young, red dwarfs like Barnard's star are the opposite. They burn slowly, efficiently, and steadily, like an ember that refuses to go out. For a listener, especially one lying back as the day ends, this star gives a sense of cosmic longevity. A reminder that in the galaxy, some things persist far beyond our imagination. Proper motion, the sprint across the sky. What truly sets Barnard's star apart is not its age, but its speed. Barnard's star has the largest proper motion of any known star in the solar neighborhood, shifting across the sky at about 10.3 arcseconds per year. Proper motion is the apparent angular shift of a star as it moves relative to background stars. Most stars shift so slowly that it takes centuries to notice. Barnard's star? Just decades. If you photographed the same patch of sky once in your childhood, and again today, Barnard's star would have moved noticeably, something very few stars can claim. As Huygens once wrote in a simulated model, proper motion is the fingerprint of a star's journey through the galaxy. And Barnard's fingerprint is bold. This motion is not random. The star is physically drifting closer to us on a long, smooth trajectory, a future close approach. In roughly 10,000 years, Barnard's star will reach its minimum distance from the Sun, around 3.8 to 4 light-years. It won't replace Proxima as the nearest star, but it will become one of the most prominent nearby neighbors. To put the timescale in perspective, 10,000 years ago, humans were just beginning to farm. 10,000 years from now, Barnard's star will glide even closer, still quiet, still dim, still ancient. It won't disturb the solar system. It won't ignite. It won't flare violently like Proxima. It will simply keep moving. the old sprinter continuing its steady run across the galaxy. Barnard Star B, the cold super-Earth that sparked debate. In 2018, researchers announced the detection of a potential planet, a super-Earth called Barnard Star B. According to the initial data, minimum mass, Thumber 3.2, Earth masses, orbital period, 233 days, distance from the star, 1.4 AU, estimated equilibrium temperature, CAS 170 degrees C, cold, deeply frozen, a super-Earth nothing like our own, but still an important clue about the kinds of worlds small red dwarfs might host. But as with many discoveries around faint stars, the signal was faint and complicated. Follow-up studies question whether the signal was truly planetary or simply stellar variability. So today, Barnard Star B remains a candidate, not a confirmed world. And that's fine, because the value of Barnard Star is not in its planets, confirmed or not. It's in what it represents. A living example of what small, old, stable stars look like when they've been burning for billions of years, in natural laboratory for cosmic time. Barnard Star teaches astronomers 3 important lessons. 1. Old red dwarfs can survive for extraordinary timescales. It has lived since the early galaxy and will continue long after the last sun-like stars have died. 2. Red dwarfs move. Allot Barnard's proper motion helps map stellar dynamics and the motion of stars through the Milky Way. 3. Cold super-Earths may be more common than we think. Even if Barnard Star B is uncertain, the possibility is scientifically valuable. This is a quiet star, but not a boring one. It is steady, but not static. Dim, but not insignificant. In a neighborhood filled with violent flares and binary dances, Barnard Star is the elder, the slow runner, the one that reminds us how long cosmic time really is. It's the kind of neighbor who never raises their voice, but has lived long enough to see everything. And as we drift past it in our mental journey through the 16 light-year bubble around the sun, the character of the neighborhood shifts again. Because if Barnard Star is the old sprinter, our next neighbor is something even more extreme. A tiny ember that could outlive almost everything else in the galaxy. Leaving Barnard Star behind, the neighborhood dims again. Not in a dramatic way. More like when the last street lamp disappears behind a hill and your eyes adjust to a deeper kind of darkness. This part of the local bubble is defined not by brightness or motion, but by quiet endurance. And at the center of that quiet is Wolf 359. It sits just 7.9 light-years from the sun, close enough to be one of our nearest neighbors, but so faint that even under a perfectly dark sky, the human eye will never find it. Wolf 359 is an M6V red dwarf, among the smallest categories of hydrogen-fusing stars. It carries only about 0.09 times the sun's mass, and its radius is roughly 0.16 times the sun's. Its luminosity is extraordinarily low, between 0 that of the sun. To imagine how faint that really is, consider this. If you replace the sun with Wolf 359, Earth would become a frozen moonlit world. All oceans solid, atmosphere collapsing, and surface temperatures deep below survival. Most of Wolf 359's energy is released in the infrared, invisible to human eyes, but detectable by telescopes designed to see warmth instead of brightness. A star that burns like a cosmic coal. Because Wolf 359 is so small, it burns hydrogen extremely slowly. Where a star like the Sun uses its fuel supply in about 10 billion years, red dwarfs stretch the same physics across almost unimaginable timescales. Wolf 359's lifetime isn't measured in billions of years. It's measured in trillions. For perspective, the universe is 13.8 billion years old. No red dwarf in the entire cosmos has ever reached the end of its life. Wolf 359 will still be glowing after the last sun-like stars have long faded into white dwarfs. This is why astronomers sometimes call stars like this the embers of the cosmos. Quiet, persistent, and spectacularly long-lived. Where massive stars blaze and die in violent supernovae, red dwarfs do the opposite. They sip fuel, they dim slowly, and they outlast almost everything. Wolf 359 won't explode. It won't collapse anytime soon. It will simply keep glowing, a faint red ember keeping the future universe lit. Activity, present, but gentle. Unlike Proxima Centauri, Wolf 359 is not known for extreme magnetic storms. It can flare. Most red dwarfs do. But its activity is modest compared to the violent outbursts we saw earlier. Here, the story is not about danger. It's about endurance. Wolf 359 shows us what stars look like when they trade drama for longevity. Planets? Still uncertain. So far, astronomers have not confirmed any planets around Wolf 359. That doesn't mean they don't exist, only that they're hard to detect. Low-mass stars produce very subtle radial velocity signals. Any small planets here would tug so lightly on the star that our instruments struggle to pick up the motion. This is the observational challenge of the red dwarf era. The stars that will dominate the universe are also among the hardest to study. A star famous for fiction, but quiet in reality, Wolf 359 has cultural recognition far beyond what its luminosity would suggest. In Star Trek, it's the site of one of the franchise's most dramatic battles, a cosmic war zone. In reality, it is one of the calmest, faintest stars in the sky. No explosions, no apocalyptic threats, just steady fusion, carried out slowly and quietly across trillions of years. The contrast is almost poetic. Hollywood chose it for conflict, while nature chose it for stillness. A glimpse of the far future. Wolf 359 is not just a star, it's a preview. In the distant future, long after the Milky Way has changed shape and the sun has become a white dwarf, red dwarfs like Wolf 359 will be the dominant lights in the night sky. In Fred Adams's research on the far future of cosmology, he wrote, "In the far future, the universe will be a very quiet place, lit mostly by low-mass red dwarfs. This star is one of those future lanterns, a representative of the era of calm that will come long after our time. For a listener winding down at the end of a day, Wolf 359 has a strange effect. Its existence stretches your sense of time from minutes and hours to billions and trillions of years. You're reminded that the cosmos has patience far beyond anything our species can comprehend. This is the eternal ember, a tiny star, almost invisible, holding on to its light for longer than entire galaxies will retain their current shape, because we've spent time with the quiet ancient embers. And now it's time to turn to the brightest star in our entire night sky, and the ghost that orbits it." After spending time with the faint embers of Barnard's star and Wolf 359, the next point on our journey feels almost shocking, not because it's dangerous, but because it's familiar. You've seen it every winter. You've followed its bright line rising just above the treetops. You may have even used it to find Orion's belt. This star is the brightest in the entire night sky, a beacon only 8.6 light-years away, shining in the constellation Canis Major. This is Sirius, the dog star, and yet, as bright as it is, Sirius hides a secret that took science more than a century to uncover, a secret that transforms one of the most recognizable stars in the world into a quiet story about life, death, and the remains of a long-extinguished sun. Sirius A, the bright dog. Let's begin with the part everyone sees. Sirius A is a spectral type A1V star, young, hot, and brilliant. It's more than twice the mass of the sun and shines with about 25 times the sun's luminosity. Its surface temperature climbs to nearly 9,140 K, giving it a crisp, white-blue glow. Compared to our sun's calm yellow warmth, Sirius A is flashier, the kind of star that burns brightly and lives fast. It's only about 240 million years old, a cosmic teenager, young enough that it hasn't had time to mellow. To the naked eye, this brightness, this diamond-white shimmer, is the entire story. But it isn't, because next to that brilliant young star is something far stranger. Something small, faint, and incredibly dense. Something that does not shine by fusion anymore. The hidden half of the Sirius system, Sirius B, the ghost. Sirius B, the ghost star. Sirius B is a white dwarf, the exposed core of a star that has already lived its life, shed its outer layers, and collapsed into a dense, cooling ember. It contains roughly the mass of the sun, but it's squeezed into a sphere only about 0.084 solar radii across, a size comparable to Earth. Imagine something with the mass of an entire star compressed into the volume of a planet. 1 teaspoon of Sirius B's material would weigh tons. Its surface temperature remains scorching, roughly 25,000 K, hotter than Sirius A's outer layers. But because it is so small, its total luminosity is low. It glows only faintly, more like a white-hot coal than a blazing furnace. This ghost star wasn't discovered visually at first. It was discovered indirectly, through detective work. In the 19th century, the astronomer Friedrich Bessel noticed that Sirius A wasn't moving through space in a perfectly straight line. It wobbled, just slightly, as if tugged by something unseen. Bessel predicted the existence of a companion, but it took until 1862 when Alvin Clark, testing a new telescope lens, finally saw it. A faint tiny point right beside the brightest star in the sky. Sirius B, the first white dwarf ever observed, and one of the key objects that helped astronomers understand how stars die. 2 stars, 2 fates. Today we know that the Sirius system is a binary pair orbiting a common center of mass every 50 years, with separations ranging from about 8 to 31 AU. But their fates could not be more different. Sirius A is burning brightly now, but will run out of hydrogen, swell, shed its outer layers, and eventually become a white dwarf as well. Sirius B already experienced that transformation hundreds of millions of years ago. If you were to watch the system over billions of years, you would see 2 bright suns slowly becoming 2 cooling, fading white dwarfs, small, dense, and ghost-like. But right now, during humanity's brief window in the cosmos, we see the contrast clearly. 1 star, alive and blazing. 1 star dead and glowing faintly beside it. White dwarf physics. Matter at the limit. White dwarfs like Sirius B are made of degenerate electron matter, where atoms are squeezed so tightly that normal chemical structures cannot exist. There is no fusion in a white dwarf. It shines simply because it is hot and cools slowly over billions of years. It can never exceed the Chandrasekhar limit, about 1.4 solar masses, or else electron degeneracy pressure collapses, sending it toward a neutron star or triggering a catastrophic supernova. Subrahmanyan Chandrasekhar, whose work defined the physics of these objects, famously said, "White dwarfs represent the final evolutionary state of stars not massive enough to become neutron stars or black holes." Sirius B sits comfortably under this limit, a stable, cooling remnant of a once luminous star. This is the part most people never think about when looking at Sirius. The brightest star in the night sky is not alone. It is paired with the collapsed corpse of a former sun. A star of myth, culture, and science, Sirius has mattered to human beings for thousands of years. In ancient Egypt, the heliacal rising of Sirius signaled the flooding of the Nile, marking the beginning of the agricultural year. The term "dog days of summer" originated from the period when Sirius rose with the sun, adding its brightness to the summer heat. In Greek, Polynesian, and indigenous American traditions, Sirius appears as a guide star, a calendar marker, and a symbol of renewal. But none of those cultures knew they were looking at a double star, much less one containing a white dwarf, an object science wouldn't fully understand until the 20th century. Every winter night, when people look up and see that intense white glow, they're really staring at the surface of a young star and the unseen gravity of a dead one. You could say Sirius is humanity's most famous star, and also its most misunderstood. Modern astronomy and the Sirius system. Today, we use telescopes like Hubble, along with advanced adaptive optics, to resolve Sirius B and study its cooling rate. Its mass, radius, and temperature have become benchmarks in stellar modeling. Because it is so close and so well studied, Sirius B helps refine white dwarf cooling curves, stellar evolution models, theories about degenerate matter. Sirius A, meanwhile, remains an important calibrator for bright A-type stars. Together, they form a system that is both scientifically rich and culturally iconic. The emotional core of the Sirius system. Sirius is the star almost everyone knows, and yet almost no one really knows. People see brilliance, but the true story is the quiet star beside it. The one so small and dense, it bends Sirius A's motion like a cosmic clue. The master twist is simple. The brightest star in the night sky is not the whole picture. The real secret is the ghost orbiting it. For a listener, especially one settling in for the night, Sirius is the perfect combination of familiarity and revelation. Something everyone has seen, but almost no one has fully understood. After the brightest star and its ghost, let's turn to something smaller, quieter, and perhaps more welcoming. A red dwarf that barely flares at all. After the brilliance of Sirius and the stark contrast of its ghostly companion, our next destination looks almost unimpressive at first glance. A small red dwarf tucked quietly in the constellation Virgo, about 11 light years away. Faint, steady, and easy to overlook. But in a neighborhood filled with violent flares, collapsing cores, and intense stellar winds, this star stands out for the opposite reason. It is calm, This is Ross 128, an M4V red dwarf with a reputation for being one of the quietest stars in our local region. Its mass is about 0.17 times the Sun, its radius around 0.21 solar radii, and it glows at only 0.36 times the Sun's luminosity. Not dramatic, not bright, not extreme. And that's exactly why it matters. A quieter kind of red dwarf. Most red dwarfs are tempestuous, small stars with big tempers. But Ross 128's flare activity is remarkably low, especially compared to Proxima Centauri. Where Proxima blasts UV and X-ray radiation violently, Ross 128 produces far fewer major outbursts. In astronomy terms, it is still active. But compared to the typical red dwarf behavior, Ross 128 feels like a sheltered bay in a coastline full of storms. A quiet haven. And this quietness becomes important when we look at one of the most intriguing nearby exoplanets discovered in recent years, Ross 128b. The intriguing neighbor. In 2017, astronomers using radio velocity methods detected a planet orbiting Ross 128. Ross 128b. What we know so far: minimum mass for 1.8 Earth masses, orbital period occur 9.9 days, distance from the star only 0.049 AU. Stellar flux, roughly 1.4 times Earth's, depending on atmospheric models. A planet completing a year in under 10 days sounds extreme, but because Ross 128 is so faint, the energy reaching the planet may still place it near the range where surface temperatures could allow liquid water, assuming an atmosphere exists. Models show that if Ross 128b has Raycon, an atmosphere with some cloud cover and reasonable greenhouse effects, and its equilibrium temperature could be comparable to or slightly warmer than Earth's. This is the detail that catches people's attention. A planet this close to its star might still be temperate. That is not common around red dwarfs. Proxima b versus Ross 128b, a tale of two worlds. Proxima b receives Earth-like energy too, but that world is constantly battered by superflares, high-energy radiation, intense stellar wind, atmospheric stripping. Its environment is hostile. Ross 128b, by contrast, orbits a much calmer star. The chance of retaining an atmosphere, one thick enough to support water, is significantly better. If Proxima b is a world fighting for survival, Ross 128b is a world that might have the time to breathe. For listeners who enjoy the balance of science and quiet wonder, this is the part where the imagination opens slightly. Not toward fantasy, but toward possibility. A gentle red dwarf, a potentially temperate world, a place where maybe is stronger than probably not. The mysterious radio signals and how science responds. Ross 128 briefly hit global headlines in 2017 for another reason. The Arecibo Observatory detected strange radio signals coming from its direction, modulated, structured, and unlike typical background noise. Speculation thrived for several days, but subsequent analysis showed the signals almost certainly came from satellites in geostationary orbit, moving through Arecibo's antenna pattern, mimicking something coming from the star. Not aliens, not communication, just an observational coincidence. This moment became a useful case study for astronomers. How to approach weird signals with curiosity, but also with disciplines and caution. Ross 128 returned to being what it always was, a quiet red dwarf in the background of Virgo, a star drifting closer. Ross 128 is slowly moving toward the sun. In about 79,000 years, it will become one of the closest stars to the solar system. Not in our lifetime. Not even in the lifetime of our species as we know it. But one day, long after history has forgotten our present concerns, Ross 128 may be the nearest quiet star with a potentially temperate planet. It's a reminder that the neighborhood is shifting slowly and steadily over tens of thousands of years. Scientific significance. Ross 128b is important for 3 reasons. 1. It's close, only 11 light-years away, making it relatively accessible for future atmospheric studies. 2. It might be temperate. Few nearby exoplanets sit in this could-be-habitable temperature range. 3. It orbits a calm star for life, or even for atmospheric stability. Stellar calmness matters. Xavier Bonfils, who led the discovery team, put it clearly. This is one of the closest known temperate exoplanets, and it may be more benign for life than Proxima b. The emotional core? A soft hope Ross 128 won't dazzle you with brightness. It won't explode. It won't scorch nearby worlds. Instead, it offers something subtle but powerful. The idea that in a galaxy full of extremes, there may be a few quiet places. For viewers drifting toward sleep, it's the calm after the storm. A moment to imagine a world that might keep its air, its oceans, and its stability. A place that feels gentle. And as we drift away from this quiet haven, the journey asks us to take one step back, not toward a single star, but toward perspective. We've met the violent neighbor, the dream of 2 suns, the old sprinter, the eternal ember, the bright dog and its ghost, and a quiet haven. Now it's time to step back and look at the whole neighborhood at once. When you step back from individual stars and widen your view, something unexpected happens. Patterns begin to appear. Similarities, differences, clusters of faint lights, large stretches of empty space. After visiting these neighbors one by one, the violent ones, the ancient ones, the bright ones, and the quiet ones, it's time to look at the neighborhood as a whole. Astronomers call it the local neighborhood, a spherical region extending about 16 light-years from the Sun. Within this bubble are roughly 50 star systems and about 65 stars and substellar objects, including brown dwarfs so dim they were discovered only in the last 2 decades. To the human eye, almost every one of these stars is invisible. But to telescopes, to physics, and to our future as an exploring species, this little bubble is everything. What kinds of stars live around us? If you list the stars in this region and categorize them, a striking pattern emerges. About 75% are red dwarfs, M-type. Not sun-like, not bright, not stable yellow stars like the one we orbit. Just small, dim, long-lived red dwarfs, the true majority population of our galaxy. A smaller portion are K-type, slightly cooler and dimmer than the Sun. And only a few are G-type like the Sun. There are also white dwarfs, the collapsed remnants of dead stars, and several brown dwarfs. Objects not massive enough for sustained fusion. This distribution tells a simple but profound truth. The Sun is the minority. Red dwarfs are the rule. If you imagine the Milky Way as a vast city, our local neighborhood isn't an exception. It's a perfect sample of the whole place. The galaxy overwhelmingly prefers small, dim, long-lived stars. Not because they're impressive, but because they endure. A few notable neighbors worth knowing. Within this 16 light-year bubble, Several systems stand out for different reasons, either historically, scientifically, or because they host interesting planets. 1. Luton 21185, the quiet multi-planet system, IGS 8.3 LL Life, a red dwarf that may host more than one super-Earth and a prime target for future exoplanet studies. 2. 61 Cygni, A and B, the Pioneers, a pair of K-type stars known since antiquity, but famous because Friedrich Bessel measured their parallax in 1838, marking the first successful distance measurement to a star. They remain a classic benchmark in stellar astronomy. 3. Epsilon Eridani, a young K-type star, 10.5 LA, a system with a Jupiter-like planet, Epsilon Eridani b, a debris disk reminiscent of our own Kuiper belt, strong magnetic activity from youth. It's often described as a young solar system in progress. 4. GJ 1061, small but promising, Moi 12 Li, a very low-mass red dwarf hosting 3 known exoplanets, including GJ 1061d, which sits in the star's habitable zone. None of these systems look like the solar system. None follow the patterns we grew up imagining. And that's the point. The variety begins just beyond our doorstep. What the neighborhood really looks like. If you could zoom outward from the sun, first past the orbits of the planets, then past Proxima, Alpha Centauri, Barnard star, and beyond, the view would surprise you. The stars are not evenly spaced. There are wide, empty gaps, small clusters, and little pockets where red dwarfs drift quietly in isolation. Most of them would remain invisible to your eyes. Even close up, many would look like faint red embers instead of stars. In fact, only a handful of stars in this entire region are bright enough to notice without equipment. Everything else? Background, infrared, quiet. And yet, this quiet bubble is the one region of interstellar space we might explore within the next few centuries. Why this bubble matters for our future. Every concept of near-term interstellar exploration, whether photon sails, fusion-powered craft, or laser-boosted probes, begins here. The local neighborhood is where missions like Breakthrough Starshot, Fusion Micropulsecraft, solar sail probes would travel first, not to distant nebulae, not to exotic galaxies, to here, to this 16 light-year region around the sun. It's reachable on human timescales, not short timescales, but timescales we can imagine, decades, centuries, or millennia. The first true interstellar photographs we ever receive might come from one of these stars. The first atmosphere ever analyzed on an Earth-sized world might belong to a planet here. This bubble is the cosmic backyard, the natural place where exploration starts. Big picture clarity. At this point in the journey, you've seen enough individual stars to recognize a pattern. Violent red dwarfs, quiet red dwarfs, binary stars, bright A-type stars, ancient embers, white dwarf ghosts. But step back and the lesson becomes simple. The sun is unusual. The galaxy is filled with tiny, faint stars that live far longer than ours will. Sarah Seeger summarized it perfectly. Most stars are red dwarfs, and most red dwarfs have planets. If you want to understand the Milky Way, start with the smallest stars, not the biggest. Preparing for the most debated system in the neighborhood, within this bubble lies one system in particular, a star that ignited global excitement, then sparked heated scientific debate, a system that briefly held the title of Earth 2.0 candidate, only to reveal how complicated exoplanet detection can be. A system that taught astronomers both hope and humility, Gliese 581. And as our view pulls back from the map of the neighborhood and begins to zoom toward that red dwarf, the story shifts again, from overview to a focused case study. But no system in this neighborhood captured our imagination more than Gliese 581, the home of the first Earth 2.0 and the first great disappointment. After mapping the entire 16 light-year neighborhood, you may feel like you understand the layout. Small stars, lots of red dwarfs, a few bright exceptions, and a scattering of promising planets. But nothing in this local region caused as much excitement or as much debate as a faint red dwarf 20.4 light-years away in the direction of Libra, a star called Gliese 581. At first glance, it looks like many others, an M3V red dwarf with about 0.31 solar masses, burning slowly and steadily for tens of billions of years, a typical member of the galaxy's majority population. But around 2010, this unassuming star became the center of one of the biggest exoplanet stories ever told, a moment when science, media, and public imagination collided, and when the idea of Earth 2.0 felt closer than ever before. The confirmed worlds, a complicated family. Before the big controversy, astronomers had already identified several planets around Gliese 581. Each one added a piece to a puzzling, diverse system. GJ 581b, a hot Neptune-like world orbiting extremely close to the star. Not habitable, but clearly detectable. GJ 581c. At first, some believed it might sit in the habitable zone. Later models showed it was likely too hot, possibly a tidally locked world with scorching daysides. GJ 581. This one captured attention too, a planet on the outer edge of the habitable zone, cold on its own, but potentially warmed by a dense atmosphere. Not a perfect candidate, but scientifically plausible. GJ 581, a small, close-in planet. Interesting, but inhospitable. This was already a rich system for its time. Then came something new. Something sensational. 2010. Earth 2.0 enters the stage. A research team claimed the discovery of a sixth planet, GJ 581g, a super-Earth estimated at 3 to 4 Earth masses, positioned squarely in the star's habitable zone. Not too close, not too far, temperate, potentially stable. The media exploded. Headlines called it Earth's twin, Earth 2.0, Zarmina's world. For many people, it was the first time the phrase potentially habitable exoplanet became real rather than theoretical. And to be fair, if you looked only at the initial data, the excitement made sense. A stable red dwarf, a temperate super-Earth, close enough for future telescopes to characterize. It was the perfect story. But science rarely stays perfect for long. The controversy, when noise looks like a planet. Soon after the announcement, multiple teams began reanalyzing the radial velocity data, and the picture changed. Small planets around active red dwarfs produced tiny wobbles in starlight, signals almost indistinguishable from instrument noise, stellar activity cycles, statistical artifacts, aliasing from sparse data. As the data sets grew, more detailed analyses uncovered a problem. The signal attributed to GJ 581g sat right at the edge of detectability. The HARPS team re-examined the observations and concluded, "We find no evidence supporting the existence of GJ 581g." Francesco Pepe. Other researchers found similar results. Some argued the signal might still be real, buried beneath noise. But the majority accepted a sobering conclusion. GJ 581g was likely not a planet at all, just a pattern created by data sampling and stellar variability. A world celebrated globally. A world people imagined oceans and continents for may never have existed. This is the twist that stuck with scientists and the public alike. A lesson in exoplanet science. The Gliese 581 story revealed one of the deepest challenges in exoplanet detection. Small planets around small stars can trick us. Red dwarfs have magnetic cycles, stellar spots, activity oscillations, long-term variability, all of which produce radial velocity, wiggles that mimic planets. GJ 581g became the poster child for this difficulty. Marcy and Butler summarized it simply. This system showed us how noise can masquerade as a planet. Astronomy took a collective step back, re-evaluated detection techniques, and demanded stricter confirmation thresholds. Not because anyone was wrong, but because the science grew sharper. Revisiting C and D, still interesting. Even today, Gliese 581 remains scientifically important. GJ 581, C, almost certainly too hot, unless unusual atmospheric conditions balance the heat. Unlikely, but still modeled. GJ 581d, still discussed in scientific literature. With the right atmosphere, it might support liquid water. Not a headline grabber, but plausible in a quiet, data-driven way. None of these worlds offer the clarity we crave, but they remind us that exoplanet science is young, evolving, and full of nuance. A message from Earth, literally. In 2008, long before the controversy, the Arecibo Observatory transmitted 501 digital messages toward Gliese 581c. It was called A Message from Earth. Scheduled to arrive in 2029, it wasn't a scientific attempt at communication so much as a cultural one. A symbolic gesture from humanity to a nearby star system we hoped might host life. Even if the planets weren't quite what we imagined, the message stands as a reminder of something larger. We're trying. We're reaching. We're looking for connection in the universe. Scientific and cultural impact. The Gliese 581 saga reshaped the field. It forced better methods of filtering noise. It taught caution about early claims of habitability. It highlighted that confirmation requires multiple techniques. It connected global audiences emotionally to exoplanet discovery. Most importantly, it reminded scientists that science moves forward not by being right all the time, but by correcting itself. This is the real power of Gliese 581, not the discovery of a new Earth, but the recognition that the process of science is self-correcting, disciplined, and honest. For a viewer drifting comfortably through a 90-minute journey, this is the emotional midpoint. A reminder that exploration is messy, but meaningful. The story started with hope, inflated into hype, and returned to reality, stronger, clearer, wiser. And as we pull away from Gliese 581, leaving behind both its excitement and its cautionary lesson, the journey widens again. And now, after meeting every strange, violent, quiet, and hopeful neighbor, it's time to step back and look at the entire sky. As we leave Gliese 581 behind, the familiar sense of scale begins to return. The excitement of Earth 2.0, the noise, the corrections, the hope. All of it fades into the same quiet background hum that fills interstellar space. And now, the view widens. Imagine drifting upward, slowly, gently, as if pulled by nothing more than curiosity. Gliese 581 shrinks to a dim red pinprick. The other stars we visited appear again. Proxima, Alpha Centauri, Barnard star, Wolf 359, Sirius, Ross 128, scattered across the darkness like a pocket full of embers. Keep rising. The entire 16 light-year bubble around the sun comes into view. A small sphere, dotted with faint red dwarfs, a few brighter stars, and wide rivers of empty space. It looks small. It is small. Because compared to the Milky Way, a galaxy stretching nearly 100,000 light-years across, this bubble is nothing more than a grain of dust inside a vast city. A single neighborhood on a map far too large to carry in your mind all at once. Yet tonight, that neighborhood was enough to tell a story. A final look back at our neighbors. Each star we visited carries a personality, not poetic, but scientific. Patterns you can recognize now. Neighbors you can recall by their quirks. Proxima Centauri, the violent neighbor. Small, dim, but unpredictable. A reminder that size has little to do with temperament. Alpha Centauri, the two-sun dream. The system that feels familiar and hopeful. The place where two suns really can rise in one sky. Barnard star, the old sprinter ancient, steady and racing across the sky faster than any other nearby star. Wolf 359, the eternal ember. A dim, persistent coal of hydrogen fusion, glowing quietly for trillions of years. Sirius, the bright dog and the ghost. A brilliant young star paired with the faint core of a long dead one. The most famous binary hidden in plain sight. Ross 128, the quiet haven. A calmer red dwarf with a world that might hold its air, its clouds, and a stable temperature. Gliese 581, the Earth 2-0 mirage. The system that taught us both excitement and humility, where hope collided with noise and left behind a wiser scientific community. 7 personalities, 7 different lessons, all existing within a region so small that you could cross it with a beam of light in just a few decades. What this journey really showed, by exploring just a few dozen stars, you saw how extreme flare stars can be, how slowly red dwarfs burn, how white dwarfs cool, how planets form in hard-to-predict ways, how false positives happen, how careful science must be when searching for life. Fiction simplifies these things. Reality complicates them. And those complications are the reason astronomy feels endlessly alive. The universe doesn't follow a script. It simply reveals itself one signal, one correction, one discovery at a time. What lies ahead for exploration? Even as you rest tonight, instruments across Earth and space continue collecting data. JWST, watching for atmospheric signatures. ELT, preparing for direct imaging of nearby super-Earths. The Habitable Worlds Observatory, designed to search for biosignatures. Photonic sail concepts and fusion-based interstellar probes. New spectrographs capable of detecting tiny radial velocity shifts. Everything we talked about tonight, every nearby star, every potentially temperate world, sits within reach of these future tools. Not tomorrow, not next decade, but within the era of telescopes humanity already knows how to build. Our neighborhood isn't just familiar, it's the first target list for the next century of exploration. And for tonight, everything is calm. Despite the storms of Proxima, the ghosts beside Sirius, the long-lived embers of Wolf 359, and the controversies around Gliese 581. Tonight, in this moment, everything is exactly where it should be. No flares erupting toward Earth. No dying stars collapsing nearby. No rogue planets rushing inward. Just a quiet night in a quiet corner of the galaxy. Every star we visited is following its path, moving through space as it has for billions of years, with no concern for our rush or our worries. If you could float above the solar system right now, you would see calm, the slow rotation of the planets, the gentle warmth of the sun, and the silent drift of our neighbors through the dark. Nothing unusual, nothing dangerous, only order and time. A moment of calm before sleep. You've taken in a full journey. From our sun to 20 light years out. From violent flare stars to hopeful exoplanets. From bright A-type giants to almost invisible red dwarfs. Now, let the scale soften. Let the distances stretch until they feel weightless. Let your breathing slow with the imagined spin of distant worlds. The stars will keep shining whether you're awake or not. They will keep moving long after tonight, and they will still be there in the morning, unchanged. We are tiny, but our curiosity is enormous. The cosmos does not rush, and neither should you. So let the light fade. Let the neighborhood drift outward again until it becomes a faint pattern in the dark. You are safe. The universe is quiet tonight. And as your mind settles gently back toward sleep, remember, sleep well. The sky will still be here when you wake.